Hello everyone, my name is Mr. Mbrove. I'm going to teach you theorem 1 and theorem 2 in Euclidean geometry grade 11. Okay, theorem number 1 says that a line drawn from the center of a second perpendicular to a chord bisects one, which means in this second OM is perpendicular to AB. So in theorem 1 we are required to prove that AN equals to MB. It means whenever you're proving, you have to know what you're given. In this statement, we're given that OM is perpendicular to AB. And we have to know what we're required to prove. In this statement, or in this theorem, we're required to prove that AN equals to MB. And whenever you're doing a proof things, you have to have a construction. You have to construct your statement or construct your triangle so that you can prove these things. So in this cycle, I'm going to construct a radii OM and OB. Therefore, going to our proof, where first of all we have to say in which triangle that we're going to prove. In this statement, we're going to prove in triangle OAM and triangle OBAM. Therefore, we're going to say what we're seeing. In this triangle, we're given that OM is perpendicular to AB. Reason given. And when we go to the next thing, we know that radius are equal. It means OA equals to OB. And after that, we know that OM is equals to OM. OM is common. Therefore, it means triangle OAM is congruent to triangle OBM. Rectangle hypotenuse side. Therefore, it means AM equals to MB. Within triangle OAM is congruent to triangle OBM. What I'm with you on the board. Okay, now we're going to theorem number 2, which is a converse of theorem number 1. A line joining the center of a circle of the midpoint of a chord is perpendicular to the chord. In here, we're given that a line joining the midpoint of a chord, it means this side equals to this side. It means now we're going to prove that OM is perpendicular to AB. When it comes to here, we're given that AM equals to MB and OM, we're required to prove that OM is perpendicular to AB. Now we're going to do our construction where we're going to construct radii A, O, and radii OB. Therefore, we're going to start with our proof. In this proof, we're going to prove in triangle OAM and triangle OBM. Therefore, we're given that AM equals to MB, it's given, and AO equals to OB, right? And after that, OM is common. Therefore, triangle OAM is congruent to triangle OBM. Resume also is equal. And then, therefore, it means OM is perpendicular to AB. Resume triangle OAM is congruent to triangle OBM. We're done with our scenario number 2.
Okay, good day, grade 11. So I'll be taking you through theorem 3 of Euclidean geometry. Okay, the theorem 3 says that the angle which an arc of a circle subtends at the center of a circle is twice the angle it subtends at the circumference of the circle. So in this theorem, we are required to prove that angle AOB is 2 times angle ACB. ACB. So before we can start proving, we need to construct a line that joins C and O. Now we can start proving. Okay. So firstly, we look at triangle AOB. Okay, we say in triangle AOB, O1 is equals to C1 plus A, reason being exterior angle of a triangle. In triangle AOB, angle O1 is equals to C1 plus angle A, reason being exterior angle of a triangle. But we look at this, but C1 is equals to A, reason being angle opposite equal sides. The sides that are equal are AO, CO, because they are radii. But C1 is equals to A, angle opposite equal sides. CO is equals to AO. So we can now say O1 is equals to 2C1. So now we're looking at in the different triangle. We say in triangle BCO, in triangle BCO, O2 is equals to C1 plus B, and but we know that C2 is also equal to B. Now it means that O2 is 2 times angle C2. Now we say therefore O1 plus O2 is equals to 2C2, 2C1 plus 2C2. Then this gives us O1 plus O2. They give us they give us angle AOB. AOB is equals to 2C1 plus C2. Say AOB. So we know that angle C1 plus angle C2, they give us angle ACB. So 2 angle ACB. Therefore, angle AOB is equals to 2 ACB. Yeah, that's. And now we'll be doing theorem 4, which states that an arc or chord of a circular substance equal angles at the circumference of a circle. We say that the angles are in the same segment of the circle are equal. Okay, we are required to prove that angle D is equal to angle C, which is angle D is equal to angle C. Okay, so before we can prove it, we must construct. Okay, here is our construction. Let me construct it better. Okay, so now we can start to prove. Okay, so we see that triangle AOB is 2 times triangle D. Reason B, angle at the center is 2 times the angle at the circumference. We're looking at ADB. Prove angle AOB is equals to angle D, 2 times angle D. Reason angle at the center is 2 times angle at the circumference. Yeah. This is similar to angle C. Angle AOB is also 2 times angle C. Angle AOB is also to angle C. This is the same reason, angle at the center is 2 times angle at the circumference. Therefore, you can conclude that angle D is equals to angle C. Therefore, angle D is equals to angle C. Wow.
Hello grade 11th, my name is Chobeka. So I will be going through theorem 5 with you guys. So in theorem 5 we are required to prove that opposite angles of a cyclic chord are supplementary. So first, when we prove, we know that we have to construct. So let's just do that right now. So we have constructed a line that passes the center O. Then we can just say that angle O1 plus angle O2 is equal to 360 degrees. Reason being revolution, because of these angles, they round up, they give us 360 degrees. So let's just write it down. And you have to write the reason, and then reason being revolution. So then when we have constructed, then we can just say now angle O1 is equals to twice angle A. We have gone through this theorem before. Angle O1 is twice angle A. Then reason being, angles at the center is equal to twice angles at circumference. Then we can again say that angle O2 is twice angle C. Reason being the same one, angles at the center is equal to twice angles at circumference. So then when we have constructed, then you have written this statement, then you are done. And we can now solve. We can just say that angle O1 is equal to angle twice is equal to twice angle A, and angle O2 is twice angle C. Then we can substitute this ones here. Let's write it down. You see, twice angle A plus twice angle C is equal to 360 degrees. You can see a reason substitution, because if we are just substituted what we have here, then we can divide both sides by 2, and this one will kill this one will cancel this one, then we remain with angle A plus angle C is equal to 180 degrees. Then we have proven that this angle and this angles are supplementary, they add up to 180 degrees. Thank you.
Off.
Theorem 6. If two tangents are drawn from the same point outside of the circle, then they are equal in lengths. So here we're going to prove that CF equals to YF. So what I'm going to do, I'm going to construct a line from center to the point F, and therefore draw radii C, O, and OY. As we know, a radius that is going to meet a tangent at the same point. At that point, it's 90 degrees. It means here it's going to be 90 degrees, and here it's going to be a 90 degree. So we're going to our proof. Our proof we're going to prove in triangle C, F, O, and triangle Y, F, O. Okay, in this triangle, OF is common. And then, as we know, in a right angle triangle, we have a theorem of Pythagoras. It means that this is our hypotenuse, base, and opposite. So OF squared is going to be equals to OY squared plus FY squared. Therefore, because we need to prove that FY equals to CF, so we have to make FY subject of the formula. It's going to be FY squared, and take this one to the other side, is going to be OF squared minus OY squared. Here is the theorem of Pythagoras. Okay, now we're going to the second triangle. In a second triangle, we're going to say that OF again is hypotenuse. OF squared equals to OC squared plus CF squared. And here I need to prove that CF equals to FY. It means what we're going to do, we're going to make a CF a subject of formula. CF squared equals to OF squared plus minus OC squared, because we're taking this one to the other side. Therefore, we've done make this thing subject of formula. As we know, CO equals to OY, they are radii. It means here we're going to change our OC to be equals to OY from the radii. It means it's going to be OF squared minus OY squared. Therefore, it means our FY squared equals to CF squared. Therefore, FY squared equals to CF squared. To remove a square, we have to move a square root. Therefore, we're left with Fy equals to CF. We're done with theorem number 6.
Sure.
Theorem 7. The angle between a tangent to a circle and a chord drawn from the point of contact is equal to an angle in an alternate segment. Tangent theorem. So then in this theorem, we are required to prove that angle RFP is equal to angle S. So then we can now construct then we can say that angle F1 is equal to angle R3. Angles opposite equal angles. Because of here and here we have radius and radius are equal. So angle F1 plus angle O4 plus angle R3 is equal to 108. Sum of angles in a triangle. So angle F1 plus angle O4 plus angle R3 is equal to 108. Sum of angles in a triangle. So then 1, 2, 3, they are supplementary. So then we can say that angle O4 is equals to twice angle S. Then the reason being twice angles at the center is equals to twice angles at circumference. So then we can substitute what we have to this statement here. Angle O4 is here, is twice, and we can say angle F1 is equal to R3. Angle R3 here plus twice angle S plus R3 again is equal to 180 degrees. Then R3 plus R3 get twice angle R3 plus twice angle S is equal to 180 degrees. And we can say angle R3 plus angle S is equal to 90 degrees. Then here we have our 90 degrees here because tan perpendicular to a radii. Then it means that angle F1 plus angle F2 is equal to 90 degrees. Tan perpendicular to a radii. Then it means that we have our 90 degrees here, we have our 90 degrees here. Then we have to prove that angle F2 is equal to angle S. It means that we have to make our F2 a subject of the formula. Then we can say that F2 is equal to 90 degrees minus F1. Then here we have angle S. We have to prove that angle S is equal to F2. Then we can make our S the subject of the formula. Then we can say angle S is equal to 90 degrees minus angle R3. Remember that our R3 is the same as F1 here. R3 is the same as F1. It means that we can say S1 S is equal to 90 degrees minus F1. Then it means that angle F2 is equal to angle S. Both equal to 90 degrees minus F1. Then we have proven that angle F2 is equal to angle S. Then Euclidean chord theorem. Thank you. Now let's do an activity together so that we can summarize what we have done there. You can feel free to pause the video and do the question by yourself, then answer you can come and check whether you have done them correct or not. So the statement says that PQRS is a cyclic chord. TR and TS and TR are tangents, and angle T is equal to 78 degrees and angle Q is equal to 93 degrees. They are given. So then our question says that 9.1, give a reason why ST is equal to TR. Why ST is equal to TR? Then we can say that 9.1. The reason why ST and TR are equal is that these lines are subtended by a same common point, which is T. Then we can say that they are subtended by a common point T. Then we have been told that TR is equal to TS. Then moving forward, we will be using this statement. Then we can calculate, given reason, the size of angle S1. Then where is S1? S1 is inside a cyclic quad. Then here is our cyclic quad. Then here is our S1. So then we know that opposite angles of a cyclic quad are supplementary. So now let's work on that. 9.2.1. Angle Q plus angle S1 is equal to 180 degrees. Given reasons, opposite angles of a cyclic quad are supplementary. So then we have been given that our angle Q is 93 degrees plus angle S1 is equal to 180 degrees. Then our angle S1 is equal to 180 degrees minus 93. Then our angle S1 is equal to, let's check it on our calculator to confirm, 87 degrees. Then let's go to the second one, 9.2. We have to prove the size of angle S2. Here is our S2. Then S2 and R2 are equal because of we've been told that this side, these two lines are equal. Then we can say that angle S2 is equals to angle R2. Then our reason will be that angles opposite equal sides. Then we can say that R2 and S2 and T, they are sum of angles in a triangle. And we can say that S2 plus R2 plus our T, which is 78, is equals to 180 degrees. Sum of angles in the triangle. Then we know that S2 is equal to R2. Then we can say that angle S2 plus angle S2 plus 78 degrees is equal to 180 degrees. Then twice S2 is equal to 180 degrees. We take this one to the other side, it will be minus 78 degrees. Then we divide both sides by 2, Then our S2 is equal to, let's take it together on our calculator. Then our answer is 51. Then it means that S2 is 51 degrees and S1 is 87 degrees. Then lastly, we have to prove the size of S3. Then we know that S1 plus S2 plus S3, they are supplementary because of they are on a straight line. And we can say that S1 plus angle S2 plus angle S3 is equal to 180 degrees. Reason being, angles on a straight line are supplementary. Then our angle S1, we have worked on it. Here it is 87 degrees plus our angle S2, we have worked on it is 51. Our angle S3 is unknown. It's equal to 180 degrees. Now we can now say angle S3 is equal to 180 degrees minus 87 minus 51 degrees. Our angle S3 is equal to, let's take it together on our calculator. Then S3 is 42 degrees. Then we are done. Thank you. And you can come. We are still going to upload more videos, so you can come to our YouTube to check more videos. So then we will look forward to see you again, class. Thank you very much.